Hello everyone, my name is Vidal, and today I will talk about Aquifer thermal energy storage, and I will focus on the efficiency of this technology, surface uplift, and the Thermo-Mechanical phenomenon. This presentation is part of a paper published in the Geothermal Energy Journal, and other authors of these papers are Sebastián Oliveira, Martin Salti, and François Martin. Aquifer thermal energy storage, or ATES, is a technology that permits to store the excess of energy, for example, from a power plant, and this heat or thermal energy is injected with an injection well in an aquifer. And then when we have a demand of energy, we extract it with a production well. For temperatures above 60 degrees, we talk about high temperature ATES. Is Aquifer thermal energy storage. Why this technology? Because it permits to balance the supply and demand of heat. It contributes to the reduction of fossil energy consumption, and because...
Perdona, las
¿sí?
Transparencias no están pasando para los que estamos online. Nos hemos quedado viendo solamente la primera.
¿Sal?
Yo en esto no soy experto.
Ya. Pues sal del PowerPoint. No, del PowerPoint.
¿Sal del PowerPoint?
Sí, sí, un momento.
Tierra.
Sí, es la divulgación.
Se me fue un poco...
Con Chrome. Si le digo compartir, si le digo
Es compartir toda la pantalla.
Es que ya está compartido.
Sí.
Bueno,
Quizás bueno abrir esta pantalla.
No,
Todo.
no, pero bueno.
Abrir el vínculo en Chrome y...
No, pero entonces tenemos que...
No tenemos permisos. A ver.
Sí, pues necesitamos el...
Si copias el vínculo tal cual está, se va a abrir de nuevo.
Sí, pero no sé, este punto vínculo.
Está en el Firefox. Está en Firefox.
El que tiene en Firefox, lo copias y pegas en ese bloque de arriba. Lo copias y lo pegas en
Ya something wrong with my camera.
Tiene que quedar apagada para salir del Firefox. Salir de la llamada.
Lo saco de aquí.
Sí.
Gracias, Marta.
De res. És que crec que si no presenten tota la pantalla i només presenten el PDF, el PowerPoint, quan encara que ells vagin passant les diapositives, per nosaltres no passa. S'ha de presentar tota la pantalla. O sigui, tot el que es vegi.
Ara quan tornem a connectar al CIDIC, a veure si així ho podem veure tot.
Vale. És que no sé, sentia que deien alguna cosa de permisos, però no sabia si es referien a això o què. I bueno, res, ja està.
Sí, ara miro a veure. Gràcies.
A ver.
Bueno, ¿nos oyes?
Sí, pero me ha cerrado la presentación. No, la otra, esta no es. Esto es un extra.
Martín, creo que es porque no estabais presentando con la pantalla completa, que solamente lo estaba haciendo desde el PowerPoint y no había puesto maximizar.
A ver, repite.
Que no había puesto maximizar.
Ya, pero espera, tenemos que... ¿Cuál es? ¿El extra slides o
El 3, sí, sí.
este?
Sí.
Hacemos la pantalla completa. Share.
Ahora,
Derecha.
a ver, espera. A ver, pasa. Ahora, perfecto. Ahora se ve todo. Genial, ahora sí.
Vamos aquí.
Sí, la verdad. So, as I said before, one of the most important advantages is because this technology permits to store large quantities of heat from power plants or industrial processes and sustainable heat sources, for example, solar energy or classical geothermal plants. What are the problems of ATS? One of them is chemistry, because temperature changes can produce the precipitation and dissolution of minerals, and this affect clogging, it can produce corrosion. Other issue is the efficiency of recovery. We can have head losses. And finally, one important issue is the uplift of the surface, because injecting hot water in an aquifer with some pressure, it can produce the uplift of the surface. So, as we see, this technology triggers a Thermo-Hydro-Mechanical mechanism, so that it is important to study. This presentation is organized in 4 parts. First of all, I will present the study case, then the methodology, in third case the results, and finally the conclusions. We have studied a pilot project located in Bern, Switzerland. This is an European project from Heat Store project, and there is a power plant, a combined cycle plant that they have an excess of heat and they want to store with wells into the underground. We have 5 wells, one in the center. This is a central well, 4 auxiliary wells at 40 meters from this central well. And 1 year of operation consists of 2 stages. First one, it is called injection, or in summer, it lasts 8 months. And what we do is to inject 25 liters per second at 90 degrees in the central well, at the same time that we extract water in the auxiliary wells. The rest of the year, in winter, for months, what we call back injection, we inject water in the auxiliary wells, 25 liters per second at 50 degrees, and at the same time we extract hot water, in this case, in the central well. So, to study this project, we have created a methodology that combines dimensional analysis that typically used for verify the resolution of nonlinear equations and Thermo-Hydro-Mechanical model. These 2 parts combine, we take into account the Thermo-Hydro-Mechanical equations. We use the energy balance equation, mass balance of solid, mass balance of liquid, and the mechanical mass, the momentum balance equation. This is the 4th equation. And with the first equation, the energy equation and momentum balance, we have done a dimensional analysis, and we have obtained a 3-dimensionless number. One of them is a Peclet number into color, and the other one with red color are the strange number. The modeling, we use CodeBright. This is a finite element code, and we use the pre and post processor JIT. And this is the plan view of the full case, that there are 4 auxiliary wells and one central well, and due to the symmetry of the case, we only study the 4 part. This is the 4 part of a central well and 1 auxiliary well. These two wells are we model with an external part. This is the well screen, and in the inner part it is oil. On the right we have the model, and there are two wells, as I said before, and we inject water in aquifer. Its thickness is about 100 meters, and above and below we have top rock and bottom rock. They behave as an aquifer. So we use linear thermoelasticity, and we have three materials: top rock, bottom rock, aquifer, and the well screen. This material, the aquifer and the aquifer, are the same material, but the aquifer is more permeable. And then we have the well screen, that this is the most permeable material in the model, and the dispersivity is higher than the rest of the other materials. The boundary conditions that we impose in the model are the next. On the model surface, we impose that pressure and temperature are constant atmospheric conditions, and on the lateral boundaries, these lateral boundaries, we impose that they are impermeable and adiabatic, and normal displacements are equal to 0. We also, on the external lateral boundaries, we have 0 vertical displacement, and on the bottom boundary, we have that 0. In the central well, and in blue color, the evolution of the liquid pressure in the auxiliary well. Both points are in the aquifer, and what we can see is that for the injection stage, the liquid pressure in the center is higher than in the auxiliary well, so water is flowing from the center to the auxiliary well, so this is what we expect, and in the back injection, it happens the opposite. So one of the dimensionless number we have worked is the Peclet number, that typically is defined as the ratio between the sum of the characteristic time of conduction and plus the characteristic time of dispersion, and in the denominator we have the characteristic time of advection. This is the formula. And here we have two lambdas. This is the bulk thermal conductivity, and this is the dispersive conductivity. This Peclet number, we have it composed into Peclet numbers. One, this is the conduction Peclet number. This is the ratio between the advection and conduction. And then we have the dispersion Peclet number, that it is the ratio between the dispersion and advection. We have applied this Peclet number, this formula, for a single well with the same properties as the burn case. We inject 25 liters per second in this well, and we represent in this graph. We have in the horizontal axis the radial distance from the center, from the well, and in the vertical axis we have the Peclet numbers. When the Peclet number is higher than 1, it dominates advection, and below 1, it can dominate or dispersion or conduction. Here we have the two components of the Peclet number. One is the conduction Peclet number, that is constant in this case, and for the dispersion Peclet number, this is a line. And the point where these two lines are equal, this point, it is when conduction begins to dominate over dispersion if we are in a Peclet number below 1. This is the representation of the full Becquerel number. And what we can see it is that in the first meters, until we reach distance equal to the longitudinal dispersion, it is the dispersion that dominates in the system. And then from this point, it is advection that dominates in the system. Now we have applied this dimensionless number for a 5-spot scheme. This is the current case. We assume radial flow, and we focus on, we studied a line, the evolution of the Becquerel number in a line that crosses the central well and one auxiliary well. This is the representation of the evolution of the Becquerel number with the radial distance. For the burn case, in red color, this is the Becquerel number for the injection, and in blue color, the evolution of the Becquerel number for the back injection. In black color, we have the previous case, the single well case, and if we compare these three Becquerel numbers, we can see that the first meters, they are the same until we reach a distance. This is the auxiliary well. The distance that we found the auxiliary well, and from this point, the Becquerel number for parent case drops to low values. So at this point, more or less, it is conduction that dominates the system. So now I present the evolution of the temperature with time in 2 points, as I said before, in the central well and auxiliary well in the aquifer. We can see that the initial temperature in the system is 20 degrees, and in the central well, the temperature increases to 90 degrees very fast because it's the temperature we are injecting in this area. And in the water we extract in the auxiliary well increases from 20 degrees to 60 degrees at the end of the injection. For the back injection, we inject 50 degrees in the auxiliary well, so here the temperature is constant, and the water that we extract in the central well decreases from 90 degrees to 60 degrees, to 70 degrees. Sorry. Assuming that the volume affected by temperature changes in the aquifer, it's like a cylinder. On the right, we can see that the radius of this cylinder is equal to 67 meters at the end of the injection, and we can see that there are head losses also on the top and on the bottom, mainly due to head conduction. And this radius of this cylinder is equal to 80 meters at the end of 1 year of operation, at the end of the back injection. Simulating 10 years of operation, we can see that the system is hotter in the area in the volume between the wells, and we see that the radius of the cylinder increases to 140 meters, and the head losses from the top and the bottom of the aquifer here are more or less about 70 degrees. 70 meters. Sorry. In order to know the efficiency of the system, we use the energy recovery factor that is defined as the ratio between the energy we extract in the system and the energy we inject in the system. And what we can see is here the evolution of this factor is that the more years the system is operating, the more efficient is our system, and this factor increases because increases asymptotically to a high value in this case. And what we see is that although the investment for this technology is high, the more year we are operating, the more efficient is the system. We also obtain in the dimensional analysis two dimensionless strain numbers. One is UT that relates the displacement due to the injection of hot water and characteristic displacement, and UP is for the hydraulic strain, and it is the displacement due to changes in the liquid pressure, and in the denominator we have also the characteristic displacement. This characteristic displacement is like a displacement that we have in the system before the injection, and representing these numbers in the Aquifer. We have that for injection. Well, UP, the hydraulic strain, it is always constant in the injection and back injection, but for injection, the thermal strain is higher than the UP, and for the back injection, UT, this dimensionless temperature strain, it is lower than UP. These numbers give us an idea of what we can find in the Aquifer. Now I present the results of the model. Here I have the thermal strain in the Aquifer, and here the hydraulic strain in the Aquifer in these 2 points, in the central well and auxiliary well. And what we can see is that the order of magnitude of these 2 types of strains are in the same order of magnitude. If we sum these 2 strains, we have the total, what we call the total strain, and we see that the strain in the central well, it is higher than in one auxiliary. Here I show vertical displacement in the model, and what we have is that the nearer we are to the surface, the higher are the vertical displacement, the uplift, and in this graph we see that in vertical axis of the graph we have the uplift, and horizontal the distance from the central well. What we see is that the nearer we are to the central well, the higher is the uplift. So the uplift, it concentrates on the top of the central well. We were interested in knowing the effect of the thermal expansion. With the model of Cockbright, here we have the vertical displacement on the top, the orange point, that reaches a value of 5 centimeters at the end of 1 year. And here the vertical displacement in red color for the Aquifer, that is a value around 2 centimeters. So to see the effect of the thermal expansion, we made a model that we neglected the thermal expansion, the volumetric thermal expansion in solid and liquid, and we show the results. So we have that in the Aquifer, without taking the thermal expansion, we have that vertical displacement reduces to 1 centimeter. So we see that in the Aquifer there is an effect of the thermal expansion, but on the surface, the vertical displacements are almost the same that the base model. No? We take into account the thermal expansion. Finally, the conclusions. We have presented the study of the consequence of heat storage in high temperature aquifer thermal storage that combines a 3D Thermo-Hydro-Mechanical finite element modeling and dimensional analysis. This dimensional analysis, we have obtained 2 types of dimensionless number. One is a Beckett number that permits to define not only the existence of different heat fluxes, but also the area of dominance. The dimensionless strength number, one for the thermal loads and the other for the liquid pressure, give us an idea of what the strains in the aquifer. For the very case, we have seen that inside the auxiliary wells, between the central well and the auxiliary wells, it is advection and dispersion that governs on the aquifer, and for larger distance, it is conduction. The system is more efficient in terms of energy recovery after longer time in operation, and both thermal and hydraulic loads have an important effect on the displacement within the aquifer, and the uplift is concentrated near the central well at the surface. We think that this methodology on the dimensionless number can be extended to other geoapplications related with the injection of and extraction of fluids. Could be, for example, in classical geothermal energy. And this is the end of the presentation. Thank you for your attention.
Okay. Questions or comments? Yeah. Sorry.
I have some questions. Thanks, Ruben. Very nice presentation. When you show the vertical displacement, that uplift that you observe, it's a very huge number. I mean, it's quite a big number, 5 centimeters. So this is calculated at a certain time. I didn't get it, but
this or this one.
Here you have 5 centimeters. Okay, yeah. Then in the next slide you show. Okay, so you show here the 12 months, right? Okay.
Yeah.
So because you have shown that the efficiency of the system changes during the time, and you have kind of the best results is for late time. What happened, or do you have any idea of what happened with this kind of problems with time? So are they going to increase?
With the uplift, no? You mean?
For the uplift.
Yeah, because we are using linear thermoelasticity. So at the end, the uplift then it decreases to a value and it returns to 5 centimeters. So
it returns to 5 centimeters.
Yeah, more, yeah.
Makes sense.
But there is a sort of oscillation because injection, extraction of the.
Yeah, but does it? Because at some point you get a kind of stabilized system in it, like in temperature variation. So at some point, even the variation of deformation should smooth out. I don't know. Maybe I would expect less of oscillation at some point. But I understand that it's not easy to.
You have it for because this is for
1 year.
1 year.
Yeah.
You don't get the same figure for, or you've looked at it for 10 years?
Yeah, no. But there are, it's linear thermoelasticity, so we see the same, more or less.
Yeah.
Thermo-Hydro-Mechanical.
Linear thermoelasticity.
Yeah, they have the liquid and the strain pressure liquid, so I was confused. So it's elasticity.
Yeah.
Bio?
Eh?
Bio?
Yes, bio. Yeah, bio low and yeah. Biot.
Yeah.
Biot equation and yeah. But when you calculate you isolate the thermal effects from the pressure effect.
Yeah.
So you just do kind of rest of results, or are you doing like are you running hydromechanical models versus Thermo-Hydro-Mechanical models?
Yeah, well, this is a Thermo-Hydro-Mechanical model, but we neglect the thermal expansion, but what we do it to reduce 1,000 times the volumetric thermal expansion coefficient.
Okay.
So in the end, it's a Thermo-Hydro-Mechanical. So there are changes in temperature, but the solid, it doesn't expand due to the temperature changes.
Okay.
Just one comment on the backlight number.
Yeah.
Because you put something like the sum of two. Yes. It's you say the sum of the conduction time and the dispersion time, but you cannot sum the two times. I think that equation is wrong.
It's wrong.
You cannot sum the conduction and dispersion time. You what you can do, because the third or the term to the right, let's say the 2PP at PSLB plus LD, that's correct.
Yeah.
But that's not the sum of the two.
It's true, no?
Yeah. Okay. I don't know where it's in the paper.
No, in the paper, it's written in this one.
Okay, some other questions? People from the so anyone from the audience online? No? Then okay, then I thank you again for this presentation. Okay, Yufei.
Yeah, Martin, hello. Can you hear me? Yeah. Can you hear me? Can you hear me?
Yeah, we can hear you.
Yeah. I have a question about the difference between conduction and dispersion. What's the difference between conduction and dispersion? Does the heat has dispersion?
The process or the formula or
Well, maybe the formula.
Maybe the formula. And you said the Piclet number and
Okay, you put give the equations of the.
I got the equation at the when you showed the
I couldn't.
The difference between the lambda B and lambda D.
Yeah. Sorry, share the screen. Share the screen. I think I couldn't read your screen.
Share screen.
Yes. Okay.
Share.
Yes. Oh, thank you. Thank you.
so lambda B is the bulk thermal conductivity. This is the classical lambda for thermal conductivity. And lambda D, it is the dispersivity.
How to calculate the dispersivity could you show me the governing equation? Like dispersivity, how to calculate the heat dispersion? Heat dispersion. I have no idea. I have no idea about the heat dispersion.
This is a little bit like a diffusion. Okay, so you have one coefficient, the lambda B. Okay?
Yeah.
And the lambda D is it's like a dispersion, which is a dispersivity multiplied by velocity of the water. So it is very similar as dispersion in solute for solids. So you have dispersivity, velocity, and a sort of diffusion. And the units are a little bit different. You have to multiply by the difference for heat is that let's say diffusion, the conduction is much more important than diffusion for solid. Okay.
Yeah. Okay. Anyway, I will check the paper. I couldn't see I don't know how to calculate the dispersion term. Dispersion in heat. For me, I think dispersion only appears in the mass transport, not the heat transfer. I think. I'm not sure. I will check.
It can also be in the heat transport.
Okay, I will check.
It's sort of the same equation.
Okay.
But it's a sort of deviation. Is it sort of, you can see it as the deviations?
Yeah, it is like.
I think it's sort of from knowledge.
Of course, this is also very questionable. This is just the affection dispersion equation applied to heat. So there are many people who say it is wrong, okay? But it is it is still, well, I wouldn't say completely wrong, but it is still used, let's say.
May I
Yep.
add something? I just wanted to add that the concepts of diffusion and dispersion are quite different in the sense that you can have diffusion even if you don't have flow.
Yeah.
While you have dispersion only if you have flow, because it comes from the heterogeneity of the flow, of the fluid flow. So essentially we introduce this dispersivity term in the equations, which is a way of considering that the fluid flow will be not exactly homogeneous, but we will have some heterogeneity, and so we introduce this kind of this term to take into account these effects.
But do you introduce, or it just comes naturally?
I mean, the equation is a model of the reality. No? So the advection dispersion equation, there is this part with the dispersivity term that is a way of taking into account this effect at large scale.
But the dispersion is, I don't know, a very classical way to treat this heterogeneity.
Yeah, but for example, if you want to just solve if you go to the very small scale and you solve all the streamlines, you don't need the dispersivity.
You don't need the dispersion.
Yeah.
It's what?
Well, thank you, Martin. Thank you, Ruben.
I was saying, as I see it, it's not something that you can just add to an equation. So we are here in a large scale, so this comes probably from the core scale, upscaling to the larger scale.
Maybe you're right, but people do. And I think that's another discussion.
Yeah,
I'm
but
not saying it's wrong, just say that it comes naturally from.
It comes naturally from.
Deviation from the mean value, again, confusing. Would be the term OBD. Or BD and the deviation.
Yeah, you can deduce it just as if it was a solid. Almost the same. Almost the same.
But for temperature, you can treat as.
I don't know whether you have the mass balance equations. If you have the.
So in the first one, we're talking about the first one.
Yeah, the first one. Okay. So this looks like a deflection dispersion equation. Only instead of a dispersivity or diffusion, we have a lambda. And we multiply by, we can also always multiply by intensity. You can apply the same theory to deduce the dispersion for.
So now there's two contribution, diffusion, dispersion.
Yes. Yeah.
So, a quick question. So, you mentioned that the aquifer was in the upper part, there was a bedrock or solid rock, and so how is it possible that the expansion of the lower aquifer is moving, displacing this rock layer on the top, 5 centimeters to the top? This is, maybe if you show this figure, no, the rectangle, no, the previous rectangle, the couple of slides before.
Yeah, but with the geometry and this kind of.
This one, yes. So.
This one. I think this is nice.
This one. So you have a top rock, you have a bottom rock, and the aquifer. And so you're injecting in the aquifer.
In the aquifer.
And what you're saying is that the aquifer expansion is moving the top rock 5 centimeters to the top.
Yeah.
How is this?
injecting hot water here with pressure.
But I'm surprised. I mean, it's a small aquifer, 100 meters, in comparison to the top rock that is 400 meters. So I'm assuming the top rock is much more dense than the aquifer, for example.
Well, in fact, the aquifer is a simplification of the reality because there are multiple layers of sandstone in Mars and place, and maybe it's not. The reality is not an aquifer like in this way we simulate it, but
Do you have the properties of the materials? Yes.
yeah, but we simplify more a lot because here the difference is the intrinsic permeability. Maybe it's not.
So for the elasticity modulus, for example, you take the same for these two materials,
Yeah.
is it?
Yeah.
And that is explaining. We expect the aquifer being more, having a higher.
Because in fact, reality is that all of these particles, what they say molassa, USM, the molasses, fresh water, and remember exactly, and this is the same material, in fact. And you inject in small layers of sandstone.
Okay, so it's not.
It's the same material.
It's the same material.
Yeah.
All right.
This is a simplification.
Okay.
In any case, the material that is deforming is the aquifer.
Yeah.
All the deformation is in the aquifer. Or you also observe some deformation in the, I think you don't even model the top rock, right?
No.
You just model the aquifer. So the aquifer deforms.
The top rock is part of the model.
Yeah. But the changes in temperature are.
No, there are no changes in temperature, but there may be deformation in
No, because also changes in pressure, they are all in the aquifer. So you have the strains, the deformation in the aquifer. But then, of course, if the top of the aquifer is moving 5 centimeters, then all the rest is moving 5 centimeters because it's just a rigid body, so you have to move it. So in the top rock, probably you don't have any deformation, or maybe just a little bit in the part very close to the aquifer. The point is that the aquifer is deforming.
This 5 centimeters, is it only at the surface, or what do you have at the top of the aquifer? Can you visualize?
This is the vertical displacement this is the aquifer, in fact. And it is moving, the maximum is localized here.
So you do have deformation in the top rock.
Yeah.
But this is because you are considering that it's all the same material, the only difference is the permeability.
Yeah.
Okay.
But you have mechanical stresses, or it only comes from pressure, pressure and thermal gradients. We also have shear.
No, it's linear.
I mean, boundary conditions, maybe for when you explain. You only have the deformation only comes from the fluid pressure and the thermal stresses, so we have also some.
Well, the boundary conditions affect to the displacement. We fix these lateral boundaries, the normal displacements and the vertical displacements, and these affect because the best we should do is to expand to have a higher model. But if we do that, then there is a lot of computational cost, and we cannot have a small elements in the aquifer, no? In the area we are injecting, and we cannot see the transport process.